Hi, everyone, and welcome to Online Lecture 21. Today, we will be talking about SPSS and the t-tests. So for the three t-tests that we've been talking about, which is the t-test for a single sample, the t-test for dependent samples, and the t-test for independent samples, for all three of those, we've really only been discussing how to calculate those by hand. But as you probably already guessed, you can actually use SPSS to calculate these as well. So we're just going to go through the interpretation for these three different tests today. Okay. So when, as a general rule, and there'll be a few general rules today, when you're doing an SPSS calculation to reject the null hypothesis, the observed value, p-value, needs to be less than alpha. And if you recall, the p-value is the probability of a false positive or type 1 error. So it makes sense that we want our p-value, we want our probability of error to be very, very small. Now, I know this sounds like it's a little bit different from what we talked about with respect to how you reject when it comes to the hand calculation, because there we want it to be more extreme. We want it to be further away from zero. Now, all of a sudden, we want to be very, very small. In fact, we want to be as close to zero as possible. And we definitely want to be less than alpha, whatever we set our alpha as. And if you remember, we typically set our alpha to 0.05 or 0.01 or sometimes even 0.001. Most typically 0.05. Okay. So we want our p-values low. Okay. Now the same exception to the rule applies that we've been talking about all along. If you have a one-tailed test and the results are in the opposite direction of what you had predicted or what the researcher had predicted, then you're not going to reject no matter what. It could be that the p-value is really, really, really low and it looks really, really, really significant, but you're still not going to reject the null if it's a one-tailed test and your results come out opposite of the predicted direction. Okay. So now, how are we going to deal with the rounding rule when it comes to SPSS output? Well, when we're reporting the t-score, we're going to just apply the rounding rule as always, and this will be nice because you should have access to the data, and if you don't, I'll tell you what the data was like. And then you're going to report all three decimal places when reporting the p-value, or the sig value, as it's often called in SPSS. So there's going to be 3 decimal places reported. You just almost always copy that down, with a few exceptions that we'll talk about. It has 3 decimal places. You're going to report 3 decimal places. And that's your p-value, or as it's called in SPSS, your sig value. Okay. So with that introduction underway, let's start by talking about the t-test for a single sample. Okay. Now, if you remember, the t-test for a single sample compares the population mean to the sample mean. So the information that we see right here is the size of the sample, 30, and the mean for the sample, 62.30, and even the standard deviation and standard error of the mean for the sample. Down here, we see our t-value, our degrees of freedom, and our sig, along with the mean difference and confidence interval. So where is our population mean? Right, we're comparing our sample mean of 62.3 to our population mean. Where is that? It's right here under test value. And this kind of makes sense because the mean was 62.3, the test value is 50, the mean difference is 12.3. Well, if I took 62.30 and subtracted 50, I would get 12.300. Okay. Now, let's come back to this sig value. Slight problem here. It's reporting it as 0. But we know that p-values really aren't going to ever be zero because we're never going to have zero error. We know that probability really doesn't get to zero in the field of statistics. So what's really going on here? Well, honestly, what's going on is that there's more numbers than it's showing you here. So if you were able to double click inside here, what you would see is that it would say something like 0.000000562. See, it's not zero. It's just a really, really small number. So how are we going to report this? Because we don't want to report it as equaling zero because that's false. Okay. So instead, we're going to report this as p less than 0.001. So if you ever see a sig value of 0.000, and this is true for any test going forward, for the t-tests, for the other tests we'll talk about after this, it's true for all of these, that you will always report a 0.000 as p less than 0.001. Okay. All right. So here's our 0.000 once again, and you can see that we're going to report it as p less than 0.001. Doesn't matter if you include that first zero before the decimal or not. As long as it says p less than 0.001. Okay. All right. Let's move on to the t-test for dependent samples. Okay, so now we have our pre-test mean of 73.73, our post-test mean of 76.50, our N, our sample size of 30. There were 30 people at the pre-test and post-test. Remember, it's the same 30 people at pre and post-test. And then we come down to the bottom when we get to some other important information. We get our t-score, our degrees of freedom, and our sig value, which is 0.074. So let's assume for the moment that our alpha is 0.05. So we ask ourselves the question, is 0.074 less than 0.05? No, it's not. So we would not reject. That would be easy. But let's look again. Notice how this is a sig for a two-tailed test. What if I'm not running a two-tailed test? What if I want to know if post-test scores will be higher than pre-test scores? Okay. Well, now I could go to the t-table. I could go to the t-table with my my DF of 29, the fact that I know that it's one-tailed, my alpha of 0.05. I could do that, but there's a far easier way than pulling out my t-table. And I'll tell you. To get from a two-tailed sig to a one-tailed sig, just divide this p-value, 0.074, by 2. Don't multiply, divide. Divide by 2. Remember, our goal for p-values, our goal for sig values is that they are as close to 0 as possible. And one-tailed tests have that advantage of allowing us more room in our tail, which translates to closer to 0 error, closer to 0 p-value. Okay, I know that's a little counterintuitive, but that's the idea here, is that when we get to be closer to 0 with a one-tailed test than a two-tailed test. Just like we have to be further in the tails for a two-tailed test than a one-tailed test, we get that little added strength that we need to our study. Now we don't need as much when we go from two-tailed to one-tailed. Okay. So let's look at that. So SPSS will only report a p-value for a two-tailed test. How do I get a one-tailed test p-value? Divide the sig value or p-value by 2. The alpha does not change. The t does not change. The df does not change. Nothing else changes. Only the sig value. That's the only thing you divide by 2. Leave everything else alone. Okay. And that's true for any t-test, and it's going to be true for any of the tests we talk about going forward. That's how you get from two-tailed to one-tailed. So as you can see in the next slide, we take this 0.074, we divide by 2, and we get our one-tailed p of 0.037. So now we can ask ourselves, is 0.037 less than our alpha of 0.05? Notice the alpha has not changed. Yes, 0.037 is. So we can reject the null that the post-test is not higher than the pre-test. Okay, all right. Now, for fun, let's just say that I had said that the pre-test was higher than the post-test. Well, I just look right here at the means, right at the top. Is 73.73 higher than 76.50? No, it's not. So doesn't matter whether I divide this by 2 or divide it by 1,000,000, I'm never going to reject that null. So I can still report a p of 0.037, but I'm still not going to reject that null because this is in the wrong direction. I said pre would be higher. What happened? Post is higher. Okay. All right. Now you might be wondering, okay, so back to our one sample t-test, when we had that 0.000 that we're reporting as p less than 0.001, what if that was one-tailed? What do I do then? You still report it as p less than 0.001. That's good for two-tailed or one-tailed when you have that 0.000 sitting there. Okay, all right. Okay. So now let's take on the independent samples t-test, which I will admit that it's the hardest one to understand, but we're going to walk through it step by step so that you can get it. Okay, so now what's going to happen on the next slide is you're going to see 3 different sig values, and you have to figure out which one to report. Here's the one not to report, never to report. It's the sig in the second column. The sig in the second column, never report that. And I'll show it to you right now. See this sig right here, the 0.441 in the second column under Levine's test for equality of variances? Nope, don't report that. But do look at it. Look at it and decide if it's greater than or equal to 0.05 or less than 0.05. If it's greater than or equal to 0.05, you're going to use the top row of values in columns 3, 4, and 5. If this value is less than 0.05, you use the bottom row of values in columns 3, 4, 5. So let's look at this to understand this. We look at this sig value, 0.441, and we ask ourselves, remember, we never report the sig value, but we ask ourselves, is this bigger than or less than 0.05? If it's greater than or equal to 0.05, I'm going to use this top T of 2.123, this top DF of 28, and this top sig value of 0.043. If this was less than 0.05, let's pretend for just a moment that this was 0.004. Instead of 0.441, it was 0.004. Then I use this bottom set of values. 1.995, 17.366 for the DF. And yes, you would report that whole number. And sig value of 0.062. Now, if this was a two-tailed test and our alpha was 0.05, what a difference that makes. Because 0.043 is less than 0.05. So we would reject the null, that there is a difference between low persons of low income and persons of middle income on the medical anxiety scale. On the other hand, if we were using the bottom set of values, 0.062 is bigger than 0.05, so we would not reject the null. Okay. Now, just to point out, these are your N. So there was 11 in our first group, 19 in our second group. Remember, you can have different size N's with a t-test for independent samples. And here's our means, 10.91 and 8.53. You can have, well, of course, there are not surprisingly different means. Could be the same, but in this case, they're different. Okay. If you're a little curious as to what this 0.441 is all about, it's telling you whether your variances are equal. Now, if you remember back to our assumptions for our t-test for independent samples, well, we said our variances were going to be equal, but that was an assumption we were making. When it comes to SPSS, it's a little bit more computationally oriented and able to do more calculated computations. Let's put it that way. In other words, it can handle unequal variances. And if this is less than 0.05, it means it's significantly different than equal. So if we don't have equal variances, we use this number, this funny, crazy DF number, and this sig value. So when we're hand calculating, we have to assume the variances are equal. Like I said, the calculations are just a bit too complicated otherwise, but SPSS can handle it. And SPSS can do this extra special t-test for independent samples for us. Okay. Now, what if this was a one-tailed test? And I said that persons who have low income would report higher levels of medical anxiety on the scale than persons of middle income. First, is my direction correct? Yes, low is higher than middle. Good. Next, am I below the value? Well, if this is 0.441, I use the 0.043 and I divide that by 2, and it's 0.022 approximately. Yep, that's less than 0.05. Sure is significant. If this was 0.004 by the Levine's test instead of 0.441, and then this becomes not 0.062, but 0.031. Yup, that suddenly is less than 0.05. Okay, all right. So again, we're asking the question if this number is greater than or equal to 0.05. If yes, use the top set of values. If no, use the bottom set of values. So again, if it's greater than, we're using the 2.123, the 28, the 0.043. If it's less than, the 1.995, the 17.366, and the 0.062. Okay. Here's one more example just to make sure we're good. So we kept the study the same. We still have 11 people and 19 people, but now we've changed up the means a little bit, and we've changed up the SIGs a little bit. So now this is 0.047. The sig value under Levine's test for equality of variances is 0.047. What do you think? Less than 0.05 or greater than or equal to 0.05? Well, I would say it's less than 0.05 because 0.047 is less than 0.05, all right? You can think of it as like 0.047 versus 0.050, 47 versus 50. But just know that it's closer to 0, right? Closer to 0 than 0.05, so it's less than 0.05. All right, so because of that, I'm using the bottom set here, 1.207, 10.452, and 0.254. Even if this was a one-tailed test, that 0.254 would only become a 0.127, I think. Anyway, it's not going to be less than 0.05. Had this not been 0.047 and this had been 0.112, then we'd be using the top set of values, the 1.572, the 28, and the 0.127. Again, even if this had been a one-tailed test, we get down to 0.064 approximately. Still not less than 0.05. So no matter what we're doing here, it's still not going to be significant. It's still not, we're still not going to reject the null. And then once again, remember, always with a one-tailed test, pay attention to the direction. In this case, we can see that the mean for low income is higher than the mean for middle income. So we got to keep that in mind. If we claim that the persons with low income will have higher medical anxiety on the medical anxiety scale than those of middle income, great. But if we claim that the other way around, that middle's higher than low, not so great. We're never going to reject the null then. Okay. So just to remind you that we want our p-values nice and low, here's where we actually buy p-values, where statisticians go to buy p-values. You can see they're all on sale. Okay. Oh, if you're wondering, just for a moment, if you're wondering when these little jokes get better, they don't. They don't. Okay, t-test for independent samples in research articles. So I think as you go through your curriculum in psychology, you probably either have encountered or will encounter research articles. And I want to just familiarize yourself with how you might see these reported. So typically the way it works is you see the letter T and then parentheses, and inside the parentheses, you'll see a number. That's the DF. Then you'll see equals, and this next number is the actual value for your calculated T. Then you'll see a comma, P less than, whatever your alpha was. If your alpha was 0.05 or 0.01 or 0.001, if this is significant, you'll see P less than one of those numbers, or it might even give you the exact P value, like we saw on the previous slide. P equals 0.047, or P equals 0.012. I should say P equals 0.0120. Let's leave it like that. So it actually has your 3 decimals. However, if it's not significant, then you can report P greater than whatever your alpha was, typically 0.05, or NS, which is, I think, the simpler one. You just report NS, which stands for not significant. Not significant. Okay. So what are the t-test limitations now that we've gone through the whole t-test shebang? What are the limitations of this? Well, the main problem is, what if you run too many t-tests on the same data question? Well, multiple t-tests in the same study increases the probability of a type 1 error, increases our alpha. How do we just adjust for this problem? Well, we could set a lower alpha, but there's a better way. And we're going to talk about that better way when we open up with our next set of material. Okay. So, but for now, what you could do if you really were stuck and had to run multiple t-tests in the same study, you could just reduce your alpha. Instead of having an alpha of 0.05, maybe you decide to have an alpha of 0.01 if you're running 3 different tests or 4 different tests. Okay. Excuse me. So I tried to compile a list here of the different Z and T test steps. As far as you can tell, we're pretty much at the end of the Z and T tests. So what are the steps that you should take? Well, start off with which test you should use, right? Yeah, it can't go anywhere until you figure that out. Then set up your hypotheses, null and alternative, and then decide if it's one or two-tailed. Now, at this juncture, you could start with the calculations, or you could find the critical, cutoff, tabled, whatever you like to call it, Z or T test value, whichever you like. I like to start with the calculations. So which step am I going to start with for the Z or T test? Remember, we talked about that, and it doesn't really apply to the Z, but more so for the T's. Am I starting with step 1, 2, 3, what have you? Okay. Which information do I have? Which information do I need? Then you calculate the Z or T test score value, right? Going through those steps. We find our tabled value, and then we're going to compare the two. We're going to compare our calculated value to our critical Z or T test value. Okay. So we're going to see if we beat, and this is all for hand calculation, by the way. You know, with the SPSS, we just talked about it. I'm giving you a summary for hand calculation. Then once you have compared the two, you're going to see if you beat what was in the table. If you're more extreme, further in the tails, further from 0 than what's in the table. Next, if it's one tail, don't forget to match the direction. Is your direction matching? Right? If you predicted higher, did it go higher? If you predicted lower, did it go lower? Okay. Then you can make your decision to reject or not reject the null hypothesis. Remember, if you want to reject and it's one-tailed, you have to beat what's in the table and make sure the direction matches. If it's two-tailed, you just have to beat what's in the table. Okay, so we make our decision to reject or not reject the null. We round our calculated Z or T test score value appropriately based on the raw data. And we report the final Z or T test score value along with potentially the DF. Okay. So I have a bit of a contest for you. I tried to come up with a mnemonic for remembering those 11 steps that I just identified on the previous slide. And the best I could come up with was this. When hyper toddlers start crying, find calming music or make rhyming rhythms. It's not the best mnemonic in the world. Can you do better? That's the question. Or even better than doing better than that mnemonic, maybe you can come up with a mnemonic or memorization device for knowing which of the 4 tests to use in a given situation. Like, how do we differentiate z-test, t-test for a single sample, t-test for dependent samples, and t-test for independent samples? I gave you that little table, but is there a clever mnemonic we can come up with for that? If you can do one of these two tasks, and you care to, send me an email with your name, your mnemonic, and an explanation of how the mnemonic applies by the due date posted in D2L. And the winner or winners will receive 5 points on the next exam. And actually, I know I just said send me an email, but I'm actually going to post this as a bonus assignment in D2L. So just load it to D2L, and the due date will be there. Okay. Despite the clear difference between the treated and control groups, something made him question the data. Yeah, I told you they don't get better. But what's my point here? My point is always be careful whenever you're working with data to look at the original data. Don't just jump into, am I going to run a t-test? Now that you're starting to get to know fancier tests, don't just jump into, am I going to run this test? Don't forget about your good old frequencies and descriptives. Okay. Now that is the end of materials for exam 2. And I ask you to go to D2L, quizzes, quiz 7. The password is 7928, and answer 1 question. Okay, so that's it for exam 2. Hope you continue to do well, stay safe, and I will talk to you next time.